So guys, in this episode, we solve the most fundamental problem of any computing system, which is a resource scarcity. Resource scarcity. It means we aren't just writing the code, we are building the foundational infrastructure that allows every other subsystem to exist. Without memory management, the CPU is the king without the kingdom. Today, we map the silicon. It means we having the CPU, but without the memory management, it's basically nothing. So memory management is the most important factor in any operating system. So in this operating system, we divide the memory management in particularly three modules. Modules three. Where is the first module? Is the physical realm. It means physical knowledge, which is basically depends on the physical realm. And the second module is the virtual illusion. And third module is the dynamic fabric. This physical realm, it is in for this physical realm, we write the code in source kernel directory and the file is a pmm.c. Why this file name is physical realm? It means physical memory management, and the virtual memory management, which is a vmm.c in same directory, and the dynamic fabric, which is meant kmalloc.c. We will see in this video why exactly we write this three code and what is the exactly meaning of this code. And we discuss first initially of our module 1, which is a physical realm. In the folder in the file which is name is a pmm.c, physical memory management. It means this is a basically a hardware inventory. We need to know exactly which 4 kilobyte chunks of the RAM frames are free and which are the occupied. It means the hardware memory having the 4 kilobytes chunks of a RAM are free or occupied. We will see in this video and the code to exactly what does this code work and how does this code work. And another which is a module 2, it means the virtual illusion. The file which is the virtual memory management. It means the physical RAM. We know the physical RAM is a messy, and it means the virtual memory is a VM virtual memory allow us to give every process a perfect world. Give process to perfect world. How? We also check in this code what it does mean perfect world. In the next and the last but not the least, module 3, the dynamic fabric, is a kmalloc.c. It means it is a physical memory management, works in the 4 kilobyte chunks. We see we saw, and kmalloc is the scalable for the small allocation. Here is a kmalloc, it is a malloc function which is a scalable for small allocation. It means we actually mapping the silicon and build the illusion of the infinite space. RAM, it means the hardware inventory. We need to know the exactly which 4 kilobytes the chunks of the RAM frames are free and which are the occupied. So we will give the name of the file which is a pmm.c inside the kernel directory and start with the function void pmm init struct multiboot underscore info mb underscore info. What exactly this we will check in spin init address of the spin lock, the address of the PMM lock, and complete it. Then mark everything as a reserve initially in a safe default. First for int I equal to 0, I less than max frames, and divide by which is our 32 I plus plus. We increment by 1 and bitmap frame underscore bitmap start with the I equal to 0. It means 0 to max frame divided by 32, and the basically address is 0xff f f f f f. Let's complete it, and then our second, which is a the multi-boot, scan the multi-boot memory map, and finding the usable silicon uint 64 underscore t and max adder which is equal to 0, and multi-boot tag iteration if entry forward entry type which is equal to equal is 1, entry type is 1 it means available RAM, 1 is equal to available RAM, and for uint 64 underscore t adder which is equal to entry forward slash adder, and adder is less than entry adder plus entry forward slash len increment by 1 the page directory page size. Inside the for loop we need to add the bitmap unset is adder divided by page size, and if this adder plus page size, if this adder plus page size is greater than max adder, and the max adder which is equal to adder plus page size. So basically, in our spin init, we exactly initialize the lock, memories, share resources. If two CPU core try to grab the same physical frame at once, the system will crashes. Okay, this is our the for first multi-core the safety measure, and there is the address which is a 0x. I think eight times f. We assume that nothing is free until the proven otherwise. This is the prevent the kernel from accidentally overwriting critical hardware region or the BIOS memory. Okay, and here is a line number 8, which is define the max adder equal to 0. It means we track the highest physical address. We track the highest physical address reported by the hardware. This allows us to optimize later loops by not scanning theoretical memory that doesn't exist. And this line number 11, it means if entry is type 1, we only trust what the bootloader explicitly label as available. And here is a bitmap unset. It means this convert our physical address into a bit index and flip it into the 0. We are initially unlocking the gate. But to that the piece of the silicon. Okay, we will start to optimize the build, optimize the fast location stack, optimize optimize the build the fast allocation stack uint 64 tree and max frame, which is equal to max adder and divide by the page size, and for uint 64 f equal to 0 and f is less than max adder divide by the page size and increment by +1. It means if there is a physical address which can convert it into a bitmap, if bitmap test f, then free stack pointer, which is equal to f into page size. What exactly this? It means here is a free stack. Instead of searching a massive bitmap every time we need to the page, it means can be the slow. We push every free address onto the stack. Now allocating a memory is just a pop operation, which having the O of one complexity. Then we initialize or the define the file for the physical memory management. Then after we working on the virtual memory management, and it can start with a void vmm map void. It will take the uh, argument pm14 and uint 64 byte p word and uint flags. pdpt, which is initialize ensure our next table uint star pm4 pml4 Given TD which is equal to ensure next table PD PT. We need to understand the physical RAM is not supporting the time. At that time, the virtual memory allow us to give the every process to the perfect world. It means the perfect allocation. Flag and page huge optimization. We need to do optimization. Huge 2 MB huge page. So PD index and the PDM index are going to virtue which is equal to 1 lakhs or page present and return given 50 ensure the next table PD index virtual and PT and the same virtue the lakhs or the page present. It means here is a line 2 and 3. It means this can ensure the next table. It means this is a recursive hardware traversal. If you want to the map a virtual address, but the subdirectory, it means the page table subdirectory. It means the page table doesn't exist. We can call the physical memory to create it on the fly. It means recursive hardware traversal. If you want to map the virtual address, but the page table doesn't exist, we call the physical memory to create on the fly. And in next line, which is the line number 5, it means if flag and the page huge, it means page huge, which can check the if we are mapping a large resource like the GPU frame buffer. And here is a line 7. It can instead of going down to the fourth level, we stop at the third level, which is a PD. It means set the huge page set bit. This maps a 2 MB at once. It's the difference between moving 512 small boxes on a one giant shipping container. Here is a line 11 and 12. It means standard mapping. We reach the final leaf of the tree and write the physical address into a page table. We reach the final leaf of the tree and write physical address into the page table. The CPU's MMU, it means memory management unit, will now hardware translate these addresses in nanoseconds, which can our optimization part. Use 2 MB huge pages. It can instead of going down the fourth level, it can stop the third level, which is a PD, and set the huge page bit. Then our module 3, which is a kmalloc. void kmalloc size underscore t size. First is a find of free block in our linked list. It means block underscore t, which can base and find the base seed. Then if block is too big, then split it. If base size, which is greater than size plus size of block underscore t plus minimum split, and split block of base size. Then mark as a use and return pointer base use, which is 1, and return. It means here is a line 3, which is a block t based find base fit size. It means we don't just take the first hole as a we find the one that fits the closest to our request. It means this minimize the memory fragmentation, the slow death of an OS. And here is a line 7, which is a split block. If we ask for the 10 bytes, but the whole is a 4096 bytes, we don't waste the rest. We cut the block and creating a new header for remaining 4086 bytes. Split block. From if base size is greater than the size plus size of the block t plus minimum split. And here is a line 12, which is a pointer match. It means we return the address. We return the address of the after the metadata header. The user doesn't need to see our internal ledger. They just need their memory. Return pointer. It means we map the silicon, build the illusion of the infinite space. We created the tools which can manage it. In the next episode, we breathe the life into the machine with the interrupts and the PIT. What exactly interrupts? What exactly PIT? We will check in our next episode. Stay deployed.